Hello everyone, welcome to the OneClass channel. My name is Marlyn. I'm a second year student at the University of Waterloo studying chemical physics and math. Today I'm going to be going through some high school level and college level chemistry problems. Be sure to check out the links in the description if you're in need of any extra homework help or would like some one-on-one tutoring. Okay, let's get into it. So for our first question, we would like to figure out how many valence electrons nitrogen has. So valence electrons are so first you need to define what the valence electrons are. And these are going to be the electrons that are most loosely held. The reason why we tend to care about them is because they are the ones participating in chemical reactions. So both inorganic and organic chemistry, when we're talking about any form of bonds, we're talking about the valence electrons because they're the ones participating. In order to start involving core electrons, that would require high energy because they're closer to the nucleus, therefore they're experiencing more of a pull than the valence electrons that are they're basically least attracted to the nucleus because they're the ones that are furthest out. And so because they're the most loosely held, that means that they are on the outermost shell. So depending on what level of school you're at when you're asked this question, if you're using the Bohr model, and let's say that we are talking about aluminum. Let's say we have aluminum here and we have 13 electrons. We know that the first shell can take 2. Second shell can take 8. So we reach 10 now, and that leaves 3 on this last shell. And so if you're using this model, you would say that aluminum has 3 valence electrons. If you're using the more accurate model derived from quantum mechanics, then you'd have the s orbitals, and that would be 1 orbital, so it can take 2 electrons. You'd have the p orbitals that are 3 orbitals, and hence it could take 2 by 3, so 6 electrons. And you have the d orbitals that are 5 of them, and so they can take 5 by 2, so 10 electrons. You have other orbitals, but we tend to stay between sp, df. And so for aluminum, our example before we get to this question, we'd need to write out its electronic configuration. You can use Madelung's rule, or Madelung's diagram, but it's summarized quite well by the periodic table. And so if I just read the periodic table, H and He cover 1s2, lithium and beryllium cover 2s2, boron all the way to neon would become 2p6, sodium and magnesium would be 3s2. And then lastly, to get to aluminum, I see, yes, I do enter the 3p area, but I'm only taking 1 step, and so it'd be 3p1. And so all of these would be forming closed shells. So the 1s2 are the 2 electrons we identified here. The 2s2 plus 2p6 add up to the 8 electrons we identified here. Then the 3 electrons on our valence shell in this older model would be the 3s2 and 3p1. So again, we would get 3 valence electrons. So this is if you're using the quantum mechanical model, and this is if you're using Bohr's model. And so we are going to use the electron configuration to figure out how many valence electrons nitrogen has. Nitrogen has 7 electrons. And so when I write it out, it would be 1s2, hydrogen, helium, 2s2, lithium and beryllium. And then when I enter the 2p area over here, I see I'm only taking 3 steps. And so it's going to be 2p3. So recall, this would form the first ring with 2 electrons, and this would form the second ring, and I can see that I have 5 electrons. So my answer would be that I have 5 valence electrons. And so if I was drawing the Lewis structure, I'd only show you the valence electrons, the electrons that are participating in anything going on around nitrogen, and I'll just draw out the 5. And that's it. Another way to answer this question is the group number tells you how many valence electrons it has. Depending on whether you call this group 15 or group 5, either way it has 5 valence electrons, all of the elements that are inside of this column. Next up, we'd like the full electronic configuration of lead. So let's just remember what the electronic configuration is. And the electronic configuration tells you the way electrons are organized into those orbitals that we previously discussed. And so again, remember that I have the ns orbitals, the np orbitals, and nd. This would just be a number like 1, 2, 3, so on and so forth, because it's a different quantum number that we use in identification. So s is 1 orbital, and so it has 2 electrons. P is 3 orbitals, so it can hold 6 electrons, and d is 5 orbitals, so it can hold 10 electrons. Now using Madelung's rule that takes into account the Pauli exclusion principle, Aufbau principle, and Hund's rule, we get this diagram. And so if we're filling them, we would fill them in this manner. And this just ensures, by following this, we're just ensuring that we're filling the orbitals of least energy before we get to orbitals of higher energy. And so if we fill them this way, we get the electronic configuration for the ground state of whatever atom we're looking at. So the lowest energy configuration. And so you'd fill 1s2, 2s2, 2p6. Let me just write that out. 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6s2, 4f14, so on and so forth. My apologies for not mentioning the f orbitals that are 7 orbitals and can hold 14 electrons, therefore. And so I can decide to figure out how many electrons I have for lead, which can easily be done by just looking at the periodic table here. And we see that we get lead. It sometimes takes a second to find things right here. And so we have 82 electrons. And so you just count all of the electrons until you hit 82. Another way to do this is to just simply read the periodic table. And so to get all the way down here, I can just count from the top until I hit lead. And as I'm counting out the orbitals. And so this is 1s2, 2s2, because this is the s block. This is the f block, this is the d block, and this is the p block. And so 1s2, 2s2, 2p6, 3s2, 3p6, all the way until you hit the lead. And so let's go about doing that. 1s2 because of the hydrogen and helium, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10 because we drop the n by 1 once you enter the d block. And we can see that reflected here in Madelung's rule, that we go from 4s to 3d, which means we're definitely on the right track. So 3d10, 4p6, 5s2, 4d10, 5p6, 6s2. Here it gets a little tricky as to which comes before, between the F and the D block, in which case it's best to just refer to Madelung's rule in order to figure it out. We see that we go from 6s to 4f, so 4f14. And so what that is covering is everything here, which has been hidden in the periodic table because we tend to not deal with them at the undergraduate level even. And then we go into 5d10 and lastly 6p2 because we see that we only take 2 steps once we enter the p block. And this is going to be it for lead. Okay, next up we want to compare the number of neutrons in potassium 39 and potassium 40. And so we need to understand that these numbers are the atomic masses. So let's actually write down the full name for both of them. So include the number of electrons. You know that potassium has 19 electrons. You can find that out by just looking at the periodic table too. So the atomic mass is caused by adding up the masses of the neutrons and protons that you have. We ignore the electrons because in the model that we currently have, electrons are known to be very, very small compared to the nucleus that contains these neutrons and protons. And so its mass is negligible compared to the neutrons and protons. And if you simply Google neutron and proton masses compared to electrons, you'll see that the numbers work out for it to be negligible. And so what that means is if I have 19 electrons and the element is neutral, then that means I have 19 protons too. And so to find out the number of protons in both of these, I'm simply going to, the number of neutrons in both of these, I'm simply going to take away the 19. And so 19K39 has 19 protons and 39 minus 19, and that will give me 20 neutrons. Potassium 40 also has 19 protons and 40 minus 19 neutrons, and that is going to give me 21. Let me just ensure I'm getting the right numbers here. Yeah, and so we can see that these two are something called isotopes. And what that means is that they have the same number of protons, but they have a different number of neutrons, evident by what we've just calculated here. And so common examples of this would be C13 versus C12. C12 is common. It's most of the carbon atoms that we interact with today. C13 was common before, and so C13 is used for spectroscopy and it's used for carbon dating too, because if you find out the amount of carbon-13 present, you can find out how old it is. And that's it for this question. Next up, we'd like to calculate the molar mass of salicylic acid that's used to make aspirin. And so the molar mass is a molar unit. The reason why you'll see names like molar mass and molar volume is you want to get them into a form that isn't dependent on the amount of matter in the system. That just makes it easier to work with when you're doing calculations in thermodynamics and so on and so forth. And so we like to convert units like mass and volume that are dependent on the amount of matter in the system into molar units. And this makes it no longer dependent on the amount of mass in the system. Amount of matter in the system. And so the molar mass, therefore, is the mass of 1 mole of a substance. And we know from Avogadro's constant that 1 mole is equal to 6.022 by 10 to the power of 23 particles. Particles, atoms, ions, molecules, whatever you're working with in this case. And so, the way that we usually calculate it is we will actually take the summation of the number of a specific atom that you have multiplied by that atom's atomic mass. And so, for example, let's say I have CO2, I would do 1 by 12.01 grams per mole. That is the atomic mass of carbon, plus 2 by 15.99 grams per mole. And I'd simply find that answer. To be 43.99. And so when I'm doing other calculations and need the molar mass for carbon dioxide, I'd simply use 43.99 grams per mole. Now let's take the case that we actually have here of C7H6O3. That means I'm going to do 7 by 12.01 grams per mole plus 6 into 1.008 grams per mole plus 3 into 15.99 grams per mole. All of these values, the atomic masses, can easily be found on the periodic table or any chemistry resource. And so for my answer, I will get 138.088 grams per mole. And so usually when you'd be actually asked for this calculation is you'd be given something like, I have 80 grams of salicylic acid. How many moles is that? And so to do that, just using, if you'd like the formula, or you can just note unit consistency. And so to find the amount of moles, I can just do 80 grams, what I have, over 138.00088 grams per mole. The grams will cancel, leaving 1 over mole, and that's going to give me moles. And then I simply do that calculation and I get a number like 0.579 moles. And so that is usually when you'd be asked to find the value for the molar mass. And that's it for this question. Next up, we want to look for the molecular geometry of NF3. To do that, first we need the Lewis structure. And then beyond that, we go to the Vesper chart in order to find out what the best structure that would minimize the energy of the molecule is. And so for the Lewis structure, I start by counting my valence electrons. So I have 5 from the nitrogen plus 3 by 7 because of the fluorine. This is going to give me 21 plus 5, so I have 26 electrons to work with here. I start with N as my central atom. It can make the most bonds, and attach 3 fluorines. And begin by filling in all of the octets. See if I have any leftover electrons to place on my central atom. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. I have 2 electrons. The nitrogen needs 2 electrons to fill in its octet. That makes the most sense. Now, in order to go to the Vesper chart and use it, I need to first know the steric number. And I can see that I have 3 bonding pairs and 1 lone pair, and so that's going to give me a steric number of 4. I should note that the notation will be AX3E because I have 3 bonding pairs here and 1 lone pair here. And so when I go to the Vesper chart, there it is. Okay. So now I go to total domains. I know the steric number is 4, and so the version of this where it's just 4 bonding pairs and isn't telling me anything about, where the steric number is 4 and not telling me anything about how many lone pairs or bonding pairs I have, that's going to be the electron geometry, and that is going to be tetrahedral. The molecular geometry will include how many bonding pairs or lone pairs I have, and so that's when I'm going to go to my specific generic formula or account for the fact that I have 1 lone pair, and so that is going to be trigonal pyramid. And that is it for this question. Next up, I want to find out how many valence electrons chlorine, bromine, and iodine have. As mentioned, I can simply look at their groups in order to answer this question. And so I see fluorine, chlorine, and iodine are all in group 17 or group 7, depending on how you read the periodic table. And so if they're in group 7, I can expect 7 valence electrons. Additionally, another way I can do this is to just write the shorthand notation, which would get rid of all of the core electrons. And so if I did for fluorine, my closest noble would be helium, and then I'd have 2s2 and then 2p5. And so all of these are valence electrons, and so that tells me that fluorine has 7. If I wanted to do chlorine, closest noble is neon, and then I'd do 3s2, 3p5. And so that tells me chlorine also has 7 valence electrons. And that's why the group method works, is because I'm counting to the same column technically. And so if they're all in the same column, they all have the same number of valence electrons. Last, I can just do iodine really quickly. So it'd be krypton as the closest noble gas. And then I would have 5s2, 5p5. So iodine also has 7 valence electrons. And that's it for this question. I'm sorry, they asked for bromine. So that would be argon as the closest one, and then 4s2, 4p5. Okay, next up, I would like the electron configuration for zinc, but the zinc ion with a 2+ charge. So in order to do this, first, I need to note that 2+ means that I am taking away 2 electrons. So it has an extra 2 protons because the neutral state is balanced between the electrons and the protons. So the charge thing makes complete sense. And so to find the electron configuration for this ion, I need to first find the electron configuration for zinc, and then I just account for this fact by taking away the 2 highest energy electrons. And so I look at the periodic table for the electron configuration of zinc. And so let's find the zinc. So it's right here. So if I put that all in, I will get a configuration of 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. Okay, and then next up, I want to take away 2 electrons in order to find the configuration for Zn2+. Now, I need to take away from... So what we usually do, and the general rule, is that to take away electrons, you take from the highest n value. If you have 2 orbitals with the same n value, you take from the lowest L value. And so this one is quite straightforward. I can see that the highest n value is going to be 4. And so I'm going to take away the 2 electrons from there. And so for Zn2+, I'm simply going to cancel out these 2 electrons, and the configuration will become 1s2, 2s2, 2p6, 3s2, 3p6, 3d10. And that's it for this question. Next up, I would like the electron configuration for tellurium. I'm already given the number of electrons. Again, I can just decide to look for it on the periodic table. It's right here, and then just count until I get to it. And so that will become 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 4p6, 5s2. Sorry, my apologies, I skipped the D group. So it's 4s2, 3d10, 4p6, and then 5s2, 4d10, and then 5p. I need to be careful and note that I'm only taking 4 steps to hit the element that I'm looking for in. So it's going to be 5p4. And that's it for this question. Next up, I would like to draw the Lewis structures for NO2Cl and NO3Cl. So let's start with this one, and then we'll get to this one right after. So as usual, count your valence electrons. I have 5 from the nitrogen, 2 by 6 because of the oxygen, plus 7. That is going to give me 5 plus 12 plus 7. And that is going to give me 24 electrons. And so in my structure, I will surround the nitrogen with the 2 oxygens and then the chlorine. I chose nitrogen as my central atom because it can make the most bonds. Number of bonds is just 8 minus the valence electrons for whatever atom you're looking at. And so for nitrogen, that is going to be 3 bonds. Oxygen, that is going to be 2 bonds. Chlorine, this is going to be 1. And this would just be the optimal number of bonds for that atom. So the number of bonds that would minimize its formal charge. Next up, I'm going to put valence electrons around each of them to fill in their octets. See if I have anything left for my central atom. I have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So I do not have, sorry, let me just ensure. Everything is okay here. Okay, and then, so since all of my valence electrons are now taken care of, because I do have 24 electrons here, let's see about the formal charge. Okay, so for nitrogen, that is going to be 5, minus it only has 3 electrons in each of these bonding pairs, so it's going to have a charge of 2+. On the oxygens, each of them, it is going to be 6 minus 1, so -1. And lastly, on the chlorine, it is going to be 7 minus 7, so that's going to give us 0. And so what this means is that I have a minus and a +2 here. This isn't the optimal structure for NO2Cl because of all of these formal charges. Optimally, I'd like just one minus charge somewhere. And additionally, the net formal charges aren't adding up the way that they're supposed to. They're supposed to add up to 0, and these ones add up to a -1. And so there's something wrong with the way that we've chosen to put electrons in bonding pairs or electron pairs, despite the fact that the valence electrons are correct. And so now let's go about fixing that by replacing certain lone pairs with bonding pairs. And so ideally, we'd like to leave the chlorine alone. We already found that it has a formal charge of 0. And so now let's start messing around with the lone pairs on these 2 oxygens to see what would minimize those 2. And so we can start by just placing a double bond here, and that would get rid of 2 electrons. And so now I have this. Nitrogen is happy, it has a full octet, and so do the rest. So the structure is obviously better than what we had before. Just ensure that all of your electrons still add up. 10, 12, 14, 16, 18, 20, 22, 24. Yes, they do. And then now we go about counting the formal charge again. And so on the oxygens, I'll have to label them now since they're different. So on oxygen 1, it's going to be 6 minus 4 minus 2, giving us a 0, so it's happy. On the nitrogen, it is going to be 5 minus the 4 electrons that it has in a bonding pair, so it's going to be +1. On the chlorine, we already found that it's going to be 7 minus 7, 0. We didn't change anything about it. And on the second oxygen, we will get 6 minus 6 minus 1. And so we're going to get -1. And so we've seen that the formal charges have come down, which is what we wanted. And additionally, they're adding up to the correct value. They're supposed to add up to a 0. We have a 0. So this is going to be a valid Lewis structure. Next up, we need to answer the question of, sorry, let's just put all of those charges in. If there is another Lewis structure for this compound that still minimizes the formal charges and counts all of the valence electrons, but I change the configuration of lone pairs and bonding pairs in some manner. And there actually is. For those who would have wondered why I chose this as the double bond, I could have as easily just decided to make this one the double bond, and that's actually going to be a resonance structure. And so now this nitrogen will be positive, this one will have a charge of 0, and this one will have a negative charge. And so these are going to be our 2 structures for NO2Cl. Next up, I have NO3Cl. And so again, count your valence electrons. I have 5 plus 6 into 3 plus 7, which is 5 plus 18 plus 7. And that is going to give me 12 plus 18. So I have 30 electrons to mess around with. So now let's put again nitrogen as my central. I'm going to connect again the two oxygens. And let's say I start with the general structure of this. Okay? Fill in all of my octets. And see if I got the 30. So I have 6 into 4 plus 8. And that is going to give me 24 plus 8, which is 32. So I have too many electrons this way. And that would make it tempting to start making double bonds, but I need to account for the fact that nitrogen can't have an expanded octet. And that's because it's only in period 2. Period 2 is nowhere near the D group, and so nitrogen doesn't have access to the ability to have d orbitals that would help make space for all of these extra electrons we're giving it by giving it an expanded octet. So it makes the most sense to move this chlorine, and instead of attaching it to nitrogen, attach it to one of the oxygens. You can pick any of them, it does not really matter which one. And so let's attach it to this one. Again, fill in our octets as we did before. See if we have any electrons left over. So we have our 30 electrons if we draw it this way, right? So next up, let's check our formal charges as we did before. So let's go about checking our formal charges. And so on these two oxygens have the same electronic configuration. This one has a different one. So on the first oxygens, it'll be 6 minus 6 minus 1. And so that's going to give us a -1. On the second oxygen, it's going to be 6 minus 4 minus 2, yielding 0. On the chlorine, it is going to be 7 minus 6 minus 1, yielding 0. And lastly, on our nitrogen, it is going to be 5 minus 3, yielding +2. So again, we're running into the same issue of A, the net formal charge is not equal to what it's supposed to be, which is 0. And additionally, we have not minimized the formal charges. This is usually an indication that you need to go back to the drawing board and adjust it with double bonds, or remove any double bonds and replace them with lone pairs. And so let's go about doing that. And so we found that this oxygen and this chlorine are already happy with their formal charges. And so it makes the most sense to not change them with any double bonds, because that would mess up the formal charge even more. And instead, let's put in a double bond with one of these oxygens. And so you can just pick any one of them. Make sure your electrons still add up the way that they're supposed to. So I will have 4 by 2 plus 6 by 2. Well, yes, they do still add up. I do still have my 30 valence electrons. And then next up, I want to check my formal charges again. So these two oxygens now have the same electron configuration, so let's label them. So the oxygen ones are going to be 6 minus 4 minus 2, yielding 0. Chlorine is going to remain 7 minus 7, yielding 0. On the nitrogen, it is now 5 minus the 4 electrons it has in bonding pairs, yielding +1. And on the last oxygen, it is going to be 6 minus 6 minus 1, yielding -1. And so I can see that the net formal charge is 0, as it's supposed to be. And additionally, I've minimized my formal charges. And so this is going to be a valid Lewis structure, since everything is now taken care of. Now again, I need to answer the question of, are there any resonance structures? So is there any way I can change one pair of electrons in a double bond like this back into a lone pair, or move a lone pair into a double bond? And I see that I can. And usually this is how you notate your resonance structures. So you'd say I have 2 electrons coming there, and I have 2 electrons now entering here. And so my second structure is going to look like this instead. And so the net formal charges haven't changed. I've simply moved the negative charge that was here onto this one, so that this one now has a neutral charge. The nitrogen is still positive, it still has the same 4 bonds that it had before. Let me just space these out a little bit. And then to just show that the resonances, I just have that sign in between them. It would usually be horizontally, not vertically. I just wrote it this way because that's how I drew it out on the page. And that is going to be it for this question. Next up, I would like the Lewis structure for the following ions. So I just need to note that if it's a negative charge, I need to add an equivalent number of electrons. It would make sense because if you have more electrons, so I've added electrons, that means that the electron to proton ratio is no longer 1:1. That means I have now more electrons, which means more negative charges than positive charges. So it goes from being neutral to negatively charged. And that would mean that a positive charge means the opposite, and it means that I need to subtract an equivalent number of electrons. And so just reverse the logic. If I have less electrons, that means I have more protons. I have less electrons because I've subtracted off electrons. And that means the ratio is no longer 1:1. I have more protons, more positive charge, and so the ion is positively charged. And so let's start with NH2 minus, when I count the valence electrons, I will have 5 from the nitrogen, 2 because of the 2 hydrogens, and then I'm going to add 1 electron because of this negative charge, which means I have 1 extra electron. And this is going to give me 8 electrons. I will choose nitrogen as my central atom. It can make the most bonds. And so now I've taken up 4 electrons. I can't place any of the extra electrons on the hydrogen, and so I'm going to place them on the nitrogen. Next up, I want to check my formal charges since all of the valence electrons have been taken care of. On the hydrogen, I have 1 valence electron minus the 1 electron it's donated to this bonding pair, and so it's going to be 0. On the nitrogen, I have 5 valence electrons minus the 4 electrons I have in lone pairs minus the 2 electrons I have 1 electron in each of these bonding pairs, and I have 2 of them. So this is going to give me 5 minus 6, and that's going to give me minus 1. This makes sense. I expected a net formal charge of minus 1 because the net formal charge should add up to the charge of whatever you're trying to draw out. And the formal charges have been minimized, valence electrons have all been taken care of. And so this is going to be the best structure. For the next one, I have H3O plus. My valence electrons are going to be 6 plus 3 into 1 because of the hydrogens minus 1. And so that becomes 6 plus 3 minus 1, and that is 8 electrons too in this case. So I choose oxygen as my central atom. It can make the most bonds. And I will now connect hydrogens to it, 3 of them. See if I have any remaining electrons. I have 2, 4, 6, so I do. I have 2 electrons left over to place on my oxygen. Next up, I check my formal charges. On each of the hydrogens, they have 1 valence electron and 1 electron inside of the bonding pair, yielding 0. And on oxygen, it is going to be 6 minus the 3 electrons it has in these bonding pairs, minus 2, giving me a positive 1. This is expected. I expected a net formal charge of positive 1, and that positive is on the oxygen. I've minimized my formal charges, the net adds up, and all of my valence electrons are taken care of. This is the best structure. Next up, I would like to determine the lowest structure for polyatomic formal, and be sure to include all resonance structures that satisfy the octet rule. So, again, I need to account for the charge when I'm counting the valence electrons. So I have CHO minus. My valence electrons will be 4 plus 6 plus 1 plus another 1 because of the charge. So just to label them so you can understand, COH minus. And so that is going to give me 12 electrons to mess around with. I'm going to choose carbon as my central atom. It can make the most bonds. Oxygen and a hydrogen attached to it. I'm going to fill in oxygen's octet. And let's say I fill in carbons too. Now how many electrons do I have? 2, 4, 6, 8, 10, 12, 14. I have too many electrons clearly. And so I can aid this by creating a double bond between the carbon and the oxygen. I can't make one between the carbon and the hydrogen. Leaving me with that, 2, 4, 6, 8, 10, 12. I have all of my electrons now taken care of. Next up, I want to check on the formal charges. On the carbon, I will have 4 minus the 3 electrons it has in bonding pairs, minus 2, becoming minus 1. And on oxygen, I will have 6 minus 4 minus 2, giving me a 0. And now this means that this formal, this structure is correct. I've minimized the formal charge. The net adds up to what it's supposed to be, and all of my valence electrons are taken care of. It would be tempting to try and change it to have the negative charge on the more electronegative atom of oxygen, but I can't do that. I can't move this double bond somewhere else to then make oxygen negative and the carbon neutral, because that would involve creating an extra bond with hydrogen. I can't do that as mentioned before. Now I need to ask myself the question of, is there any way I can move around lone pairs to... Actually, let's experiment and see and say, what if I made the carbon happy and created a triple bond here? Now we go about checking the formal charge. On my oxygen, it is going to be 6 minus 2 minus 3, giving me a positive 1. On the carbon, it is going to be 4 minus 4, yielding a 0. And on the hydrogen, it is going to be 1 minus 1, yielding a 0. So yes, I have moved the charge to the oxygen, but it's a positive charge. This is even worse than having a negative charge on a less electronegative atom. And so what I'm going to do is just take it back to how it was, because we've determined that that's the best structure. Now, back to the resonance question. Can I move any of these lone pairs into bonding pairs, or any bonding pairs into lone pairs, to maintain the number of valence electrons while also maintaining the net formal charge? My only option here would be to move 2 electrons into a bonding pair. We've seen that that would put a positive on the oxygen, and that we don't like that, and that structure is not optimal. And so this doesn't have any equivalent. It only has the one equivalent resonance structure, and that is itself. And so this is going to be our final answer. Okay, next up we want to look for the conjugate base of NH3. And so we need to remember Molar theory, acid-base theory. And that just simply defines acids as hydrogen or proton donors, and bases as proton acceptors. And so if I have, for example, H2O plus a base, I should get I should get OH minus plus HB. And so that would mean that when I'm labeling this, this is going to be my base, because I can see it's taken the hydrogen ion, and I'm going to label this my acid because it has donated that hydrogen ion to the base. Now, the names are actually partnered, and the acid will now become a conjugate base, and the base will now become a conjugate acid. And the reasoning for this is because if I reacted this with like another base, for example, that base would take the hydrogen, and so this would be acting as an acid. So a base forms a conjugate acid, something that is capable of giving away the hydrogen that is taken, and an acid forms a conjugate base, something that is capable of pulling back in a hydrogen that it's lost. And so if I write this equation for NH3, I'm looking for its conjugate base, so I'm going to be reacting it with a base, so it can donate a hydrogen ion to become its conjugate base. So that will become NH2 minus plus HB. And so as mentioned, this will be my acid, this will be my base, this will be my conjugate base, this will be my conjugate acid. And so the answer to this question is NH2 minus is the conjugate base of ammonia. And that's it for this one. Next up, we'd like the Lewis dot structure for propane. If you're familiar with your organic chemistry, from its name, you can just tell that it is an alkane, so saturated hydrocarbon, and its prefix is prop, so we can expect 3 carbons. And so since it's a saturated hydrocarbon with 3 carbons, we expect 3 carbons absolutely saturated in hydrogen. And so all of the bonds it can make, other than the ones with other carbons, are going to be with hydrogens, is what that means. I can ensure that my valence electrons are correct. And so I know that I have 3 by 4 plus 8, which is going to give me 20 electrons. If I count them here, I will have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. All taken care of. If I check my formal charges, each of the carbons have made 4 bonds, 4 valence electrons minus the 4 electrons in the bonding pairs, yielding 0. And each hydrogen has made 1 bond, 1 valence electron minus the 1 electron in each bonding pair, and that is going to yield 0 too. And so obviously this agrees that it is the best structure. If you're not familiar with organic chemistry, then if you have C3H8, you just proceed as usual, count the valence electrons. We found that they're 20. I know my central atoms will be the carbons, and so I just draw them out. I try to assign each of them with a hydrogen and connect them. And then I double check valence electrons check out. We know that they do already. Formal charges check out, and we know that they do already. And so we end with this too. And so that is going to be it. They ask for the dot structure. Always be careful, because sometimes you can get too enthusiastic that you read the beginning of the question and you think, I got it, I know how to answer this, and you don't finish. And so you lose the marks, not because you were wrong, but because you didn't finish reading the question. So always ensure you hold your enthusiasm and finish reading the question. Okay, next up we'd like C2, H4, O2, draw the Lewis structure. They've asked for one structure, and so you can draw one. This actually has many structures. If we count the valence electrons, we have 4 by 2 because of the carbon, plus 4 because of the hydrogens, and then plus 12. Because of the oxygens, we can just label this C2, H4, O2. And so this is going to give us 12 plus 12, telling me I have 24 electrons. And so let's put carbon as our central atoms because it can make the most bonds. And then let's hypothetically put both of the oxygens on one and the remaining hydrogens around everything else. Yeah, the remaining hydrogens around everything else. Next fill in all of your octets and see if your valence electrons all check out. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. And so clearly they do not. I can fix this by creating a double bond. Now, it would be tempting to put it right here and leave the structure like this, but this will not be correct because of the fact that now I have 5 bonds on the carbon, and if I do the formal charges later, I'll find out that this structure is not valid. I can go down that path and show you what it would look like. So I'd have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. And so, sorry, let me just ensure that all makes sense. Sorry, now I have 24 electrons. So now my valence electrons make sense. Double check on my formal charges. And so on each of the hydrogen, I see that they've all made one bond, one valence electron minus the one electron in the bonding pair, and I get 0. On this will be carbon 1 and carbon 2 because they have different configurations. On carbon 1, I have 4 valence electrons minus the 4 electrons in bonding pairs, yielding 0. So those are all checked out. These two have different configurations too. On oxygen 1, I have 6 minus 4 minus 2, 0. Oxygen 2, I'm going to have 6 minus 6 minus 1, negative 1. And on carbon, I'm going to have 4 minus 5, yielding 4 minus 5 yielding negative 1, 2. And so, yes, I do have a negative charge on the more electronegative one, but I'm not supposed to have a net formal charge of negative 2. And so that tells me something is wrong here. And so that means go back to the drawing board. And so since I know this configuration doesn't work, I'm just going to change a few things about it and try again. And so instead of having it like that, because I wanted to give one oxygen a double bond, I can still do that by moving the hydrogen away from it and onto that oxygen. And so now let's count out and make sure that we have the correct number of valence electrons. So I have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. I have too many electrons again. So let's actually take them off of this carbon and just leave it like that. Actually, sorry. And fix it with a double bond. And so now I have that. Check my formal charges. On each of the hydrogens, again I have 1 minus 1, yielding 0. Both of the carbons make 4 bonds, yielding 0. Both of the oxygens have made 2 bonds, yielding 0. And so I can see my net formal charge is correct. My valence electrons are all taken care of. So this is a valid structure. You can leave that as your answer. It's the answer given. But let me just show you that you can get others as your answer if you just move things around differently. So let's start with a different configuration. Let's say that instead of having the 2 carbons directly connected, I have 1 oxygen in between them and 1 oxygen at the end. Oxygen really likes 2 bonds, so I'm not going to put any of the hydrogens on it. And I only have 4 hydrogens. Fill in all of my octets. Okay, now double check everything. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. So again, I have too many electrons. I know how to fix this, especially if it's oxygen. So I'm going to fix this by putting in a double bond. Makes carbon happy because it has 4 bonds. So does oxygen because it has 2 bonds. Count them again. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. All of my electrons are taken care of. Double check on your formal charges. Each of the carbons have 4 bonds, so a formal charge of 0. All of the hydrogens have 1 bond, so a formal charge of 0. And both oxygens have 2 bonds, so formal charge of 0, 2. Formal charge is taken care of, valence electrons are taken care of. So this, again, is also a valid structure. And so we can go on to prove that there are more by just moving those oxygens around. And all of the structures that you will get, if you just do this as an exercise, are, you should be able to get this structure, which we already showed at the beginning. This structure, which we just showed. Additionally, you should be able to get this. And then you can start playing around with it and actually creating rings. Or triangles, which is also a ring. So notice in all of these, the carbons have enough hydrogens around them. If they're not connected to an oxygen, all of the oxygens have made 2 bonds. And all of the formal charges have been minimized, and you can actually count out the electrons, and they all represent 24 electrons. So all of these are valid answers to this question. Next up, we want to find out if F2 is polar or non-polar, and explain why. So as usual, begin with the valence electrons. We have 2 by 7, so we simply have 14 electrons. There is no central atom because it's just 2 fluorines. Fill in everybody's octet. I have 2, 4, 6, 8, 10, 12, 14. Enough valence electrons. Double check on your formal charges for both of the fluorines. It's going to be 7 minus 6 minus 1, yielding 0, as it should. And so this is going to be the Lewis structure. And then to get to the polar or non-polar question, I need to find out its geometry. That way I can see and figure out the symmetry of the dipoles. And so each of their steric numbers is going to be 1. There's only 1 bond that they've made. And so if I come to the Vesper theory, I can see that that is going to mean that it is linear. So it is going to be AX, and it is going to be linear. And so it's just going to be the fluorines as we drew them out. And then next up, I can draw out the dipoles. And so when I'm drawing out the dipoles, I need to think of which one is more electronegative between the two. Both of them are the same atom, A, and they both have an electronegativity of 4.0. And so because of that, the electrons are going to be pulled towards both of them equally because they both have the same tendency to pull in electrons. And that means that they're going to remain at the same point because both of the poles will cancel out. And so there's going to be a net dipole moment of 0. And what that means is that it is going to be non-polar. And that's your final answer. Next up, I want the Lewis structure for SF5. So again, count my valence electrons and account for the charge. And so I get 4 plus 5 by 7 plus 1 because of the charge. That becomes 4 plus 35 plus 1. And so I have 40 electrons to mess around with. I'm going to put the sulfur in the middle because it can make the most bonds. And just put the fluorines around it. And then next up, I'm going to fill in all of the fluorines octets and see if I have any electrons left to put on the sulfur, our central atom. And so I have 6 by 5 plus 2, 4, 6, 8, 10. So I have 35. Yeah, so I have 30 electrons plus 10. My apologies. And so I have all of my 40 electrons this way. 10. I just want to ensure everything. And so all of my electrons are taken care of this way. I can double check on my charges. And so on all of the fluorines, it is going to be 7 minus 6 minus 1, yielding 0. On the central atom, it is going to be 4 minus 5, yielding that negative 1 charge that we see. And so the negative charge will be on my central atom. So now that I have the formal charges, they're all making sense. They've been minimized. And they add up to the net of negative 1. And so this is going to be my final structure. Okay, and those are all the questions I have for you today. I hope you enjoyed today's Q&A. If you'd like to be notified of when we post on the channel again, be sure to hit the subscribe button and the bell next to it so you can get the notification. If you'd like to post questions of your own, so that we can answer them on the live stream, be sure to check out the links in the description so that you can access the OneClass page. This has been Marlyn from OneClass, and I hope to see you next time.